We are Marrjuno Group from Aerodynamic Class 2016. Before we go any further, let us introduce ourselves.
Hi, my name is Hafidz, number 035. Hello, my name is Chresko, my number is 046.
Hello, my name is Ghullam, my serial number is 004.
Hello, my name is Alvin, my number is 002.
And hello, my name is Farhan, my number is 001.
Okay, today we would like to introduce you about Juno spacecraft from NASA Jet Propulsion Laboratory. And in this video, we will give you some information about the general information of Juno spacecraft, the launching, the trajectory analysis, and the comparison of the trajectory analysis with the data from NASA.
Juno is a NASA space probe orbiting the planet Jupiter. It was built by Lockheed Martin and is operated by NASA's Jet Propulsion Laboratory. The spacecraft was launched from Cape Canaveral Air Force Station on 5 August 2011 as a part of the New Frontiers program and entered a polar orbit of Jupiter on 5 July 2016 to begin a scientific investigation of the planet. After completing its mission, Juno will be intentionally deorbited into Jupiter's atmosphere. Juno is a type of orbital satellite. It was launched in 5 August 2011 from Cape Canaveral Air Force Station in Florida. It has a dimensions of 20.1 times 4.6 meter. It was launched using the vehicle of Atlas V551 or AV029 rocket. Juno has a specific impulse of 381 seconds and it was going for a destination to the Jupiter orbit. This type of rocket has 3 stages of boost. The first stage is Atlas V SRB. This type using a solid propellant for its propulsion. Atlas V SRB has a gross mass of 40,824 kg and it has specific impulse of 275 seconds. The second stage is using the Atlas CCB rocket booster. This type of rocket using kerosene type of propellant. It has 306,914 kg gross of mass and 338 seconds of specific impulse. Then the last stage or the third stage is using the Centaur 6 rocket. This type of rocket using LOX or LH2 type of propellant having a gross mass of 22,825 kg and specific impulse of 451 seconds.
After Atlas V is being launched to the atmosphere, Juno then tried to reach its first destination, the parking orbit. We plan that Juno is parked at the altitude of 195 km above the surface of the Earth. In this interplanetary mission analysis, we are using HOHMANN transfer orbit analysis, and we divided trajectory into 3 orbits. First, because of the distance from the Earth to Jupiter is too far away and will cost lots of fuel to make a single boost, we will launch Juno to the heliocentric elliptical orbit from the pericenter of the parking orbit so that it will fly by the Earth and will get gravity assist from the Earth gravity. Secondly, after reaching the Earth and gain velocity, we make a single boost into a heliocentric elliptical orbit transfer in order to escape the Earth's gravity and Earth's sphere of influence. And the third orbit is when Juno arrives at the Jupiter's parking orbit through a hyperbolic trajectory. To make a trajectory analysis, we will need some orbital parameters to help us calculate them. Here are some orbital parameters that will be useful in the calculations. After Atlas V is being launched to the atmosphere, Juno then tried to reach its first destination, the parking orbit. We assume that the per-center altitude of the orbit is at 195 km and apocenter altitude at 226 km above the surface of the Earth. So the velocity at the per-center of the parking orbit can be calculated by using Vesiva integral for velocity. Here we have the velocity at per-center at parking orbit with 7.8 km per second.
Juno spacecraft take advantage of gravity axis from Earth to reach orbit around Jupiter by increasing its velocity without using extra propellant. It happened when Juno moved from heliocentric orbit trajectory to transfer orbit towards approaching Jupiter. The explanation is by entering and leaving the gravitational field of a planet. The spacecraft's speed increases as it approaches the planet and decreases while escaping its gravitational pull, which is approximately the same. But because the planet orbits the Sun, the spacecraft is affected by this motion during the maneuver. To increase speed, the spacecraft flies with the movement of the planet to take a small amount of the planet's orbital energy, and it will decrease the speed using flies against the movement of the planet. The sum of the kinetic energies of both bodies will remain constant.
To get the velocity at the per-center of the orbit, we can use the Vesiva integral equation, so we can get the delta V and calculate the mass needed to perform the orbital maneuver. In our group analysis, we designed that the heliocentric elliptical orbit take 2 years of the period of time, and from that, by using the equation of period, we can calculate the semi-major axis. After we get the semi-major axis, we can calculate the velocity at per-center at heliocentric elliptical orbit in respect to the Sun. And here, we get the velocity at per-center with the value of 34.9 km per second. After that, we can calculate the delta V, and we get the delta V of 27.1 km per second. To calculate the mass needed to make this orbital maneuver, we can use Tsiolkovsky equation. For this first orbital maneuver, we need 20.45 kilograms of propellant mass. For this transfer orbit, we also use an elliptical orbit, and by using Vesiva integral equation, we can calculate the velocity at pericenter and epicenter of the transfer orbit. Here, the value of velocity at pericenter at the transfer orbit is 38.618 km per second. And by subtracting the value of velocity at pericenter for transfer orbit and heliocentric elliptical orbit, we get the delta V1 for escaping the Earth's sphere of influence. The value of delta V1 is 3.718 km per second. And then we calculate the velocity at epicenter of the transfer orbit. The value of velocity at epicenter of the transfer orbit is 7.421 km per second. And by subtracting the velocity of the epicenter at Jupiter and the velocity of the transfer orbit, we get the delta V2, or the delta V2 entering the Jupiter sphere of influence, or the Jupiter parking orbit. The value of delta V2 is 14.152 km per second. And the propellant mass needed to perform this orbital maneuver is 2.796 kilograms.
The Juno satellite has two orbital trajectory phases, Firstly is the heliocentric elliptical orbit, and the second is the orbital transfer. At the first phase, our group's plan is the satellite has 2 years period orbit, with the pericenter and apocenter radius which has been explained before. That period appears based on our calculation as when it has finished 2 years period orbit. The Juno satellite will return to its original place with greater velocity than its initial. So, the boost needed to get to Jupiter can be minimized. Then, at the second phase, the orbital transfer, we assume that the path passed by the satellite is a half of an ellipse with a semi-major axis value is equal to 464090338 km. The period obtained from calculation below is approximately 2731 years. Thus, the total time period of the satellite transfer from the parking orbit to the orbit of Jupiter is 4731 years.
So here, our comparison between the final result and the actual data of Juno mission published by NASA. You can see that the period of our group calculation is 4.731 years, while the actual data is 4.846 years, and the propellant mass needed for our analysis is 23.246 kilograms, while the actual data gives 1,280 kilograms. Well, as we can see here, the period and the propellant mass needed for the mission shows a different value between our analysis and the actual data. This happens because of some assumptions we use for the analysis. Like first, we use HOHMANN transfer orbit, which is all calculation happen for two-body system problem. But as we know that in outer space, a body couldn't be analyzed by using only two-body system. And second, we use assumption for orbital parameters. For example, like the distance between the Sun and Jupiter, distance between Sun and Earth, altitude of Juno when on parking orbit on Earth's gravity axis, which are different from the real condition. This will obviously differentiate the result between our calculation and the actual data. For example, like delta V, propellant mass needed, and the orbital period. Third, we only calculate for the Juno's trajectory from the Earth parking orbit until the arrival on Jupiter. And the last assumption is we use equation to calculate our analysis from astrodynamic class that has been simplified for good.
Okay, that's all. Thank you guys for your attention and your patience. See you on the next video.
Don't forget to hit the subscribe
Bye.
button.
Subscribe,
and leave your comment.
Thank you, bye.
Bye.